screen itself, I would like to say I kind of put all my PhD work, which was based on batteries. I'm not really sure, like everybody is familiar with how the battery mechanism and all are, but I'll try to keep it simple, more like in very general words. Because even after coming here, even though I have worked with batteries, sometimes when people give presentations, I do not understand much because of there is such a vast amount of research that you can do in any field. So yeah, I will just try to keep it general. I mean, like there are so many technical terms that may be involved. So please, kind of, if you want to ask about that, do ask, and I will try my best to kind of explain. Yeah, so I will share my screen of, okay. Um, yeah, is it like, okay? You can see my screen, right?
Yes, we can clearly
Yeah.
see.
Okay, thank you again. Like to start with, really thank you for giving me this opportunity. Like first of like this kind for me, and I'm really happy to speaking about my PhD work. I mean, like it has been more like presenting in conferences and other things. So those are different, but this is different. So yeah, I'm happy, honestly, to be doing this, and I will be speaking about donor-acceptor-based conjugated polymeric materials. But before like really going into the topic donor acceptor based conjugated polymeric materials, I would like to say a little bit about donor acceptor. So, when there is a covalent bond that is getting formed, the electron density gets shared, right? So donor acceptor is basically like there is a donor atom and an acceptor atom, of course. So it can be different combinations, like an electron, basically something which can pull the electron and something which can give the electron in very simple sense. So what happens is electron density gets shifted a bit, so charge transfer becomes very easier in those kind of systems. So in a very simplest sense. So what happens is because the charge transfer is easier, the chemical kinetics is easier. So chemical kinetics is easier. Of course, from there, if I have to say, you can actually have like a faster ion movement. Right. So that is very in a very simplest sense to put the basics of donor acceptor based conjugated materials. Now, again, so I did my MSc, like I completed my masters, like bachelor's and masters in India. And then I was working because it was a COVID time and it was like a really terrible time. And so I was working, I was very happy to be working on like we wanted, there is a small lab in our university which was trying to design prototype for like COVID-19 detection device. And I was working on it and it was nice. And then I thought, let's give PhD a try. So it was sheer out of like a decision, I think, which I didn't put much thought into. Like, I'm really interested in science or something like that. I just wanted like, let's see how PhD goes because yeah, I'm like, I can probably do it. And that was all. And I was applying to different scholarships, of course, because it's difficult to do without it. I mean, like it's much easier if you're getting a scholarship, honestly. So, and I was lucky enough to get the Japanese government scholarship, MEXT, it's called in English. So, and so I joined a battery lab, and it's a polymer come battery lab. So I happened to work on polymeric materials. And from there, again, I like after completing my PhD, like between 2021 and 2024, I kind of worked for 5 or 6 months on a small project in the lab, which was based on anode coating technologies, specifically silicon-based materials, coating technologies. And then from there, I kind of went on to do my postdoc. I joined Uppsala University, and now I am working on like developing polymeric SEIs. So if I have to say what is an SEI, so uh, like we know oxidation and reduction, right? Like any material undergoes oxidation and reduction at certain potential. So electrolytes are there, and so at a very low potential compared to lithium or sodium, when the potential is very low, like 0.1, around 0.2, 0.1, the electrolyte starts degrading and it forms more like an inorganic and organic. So there are different pathways the electrolyte can degrade and then form a layer. So I mean like a reduction layer. So that is basically an SEI. So to prevent that, to I mean like reduce the amount of electrolyte that gets that gets reduced, we can actually have an artificial SEI. So that will kind of prevent an excessive electrolyte reduction. And if excessive electrolyte reduction is not taking place, so our battery can perform longer. So that is the basic idea of having an artificial polymeric SEI on top of the anode itself. And so that is one of my projects, which is quite challenging because it's very difficult to suddenly have a polymer, because polymer as such is non-conductive. So you need to think about polymer, which is conducting, and at the same time, it kind of also meets other criteria. Like I told, it should also reduce the amount of electrolyte that gets reduced. On top of it, I'm also trying to work on non-flammable electrolytes. So electrolytes right now, whatever organic electrolytes we are working is highly flammable because they are carbonate. So if in very simplest of the sense, if you take ethanol, you just, like ethanol will just is very flammable. So we don't use ethanol in batteries, of course, but we used carbonate based. But carbonate based electrolytes are equally flammable. So we are trying to go into systems which are non-flammable. So right now, if you look into the literature, mostly the non flammable electrolytes are used as additives, like in very small quantities. So even though, even though they are fine, the performance is good, but then we are not achieving a total. There is like a time that like it after a fire is there is a time, okay, like at what point the fire completely extinguishes. So that takes longer. So if we have a completely non-flammable electrolyte, there is zero chance kind of to have a fire. So, but then it is very difficult to develop a non-flammable electrolyte because as such, the performance is very bad. There are different reasons. There is like probably another story for another day where we can talk just about non-flammable electrolytes. But yeah, so now I will be just talking about mostly my PhD work because there are all like two of my works out of three have been published. One is under review. So I will be just talking a bit about that. Um, yeah. So any research, I've just put battery research over here, but for that matter, like any research, if you see, the whole idea is there are two types, okay? I mean, there is fundamental research where you try to look into the system and try to understand the fundamentals, like why something is happening or how can you make the uh, already existing materials, how can make them better by looking into certain properties. Or there is another field which is like applied mostly, uh, where it is to find better materials. Okay, like there is commercial materials, of course, but then you try to study properties of new materials, so find better materials. And what is exactly that is exactly what was my focus during my PhD because ours was more like a material. My PhD was in material sciences and more into an applied lab. So yeah, I did it in a research institute. So mostly research institutes work with developing new materials and studying properties of new materials. So that is the reason I was also working on developing new materials, and that is the donor-acceptor-based uh, polymers. Right. And so these are few of the on the right. So there are few, these are few of the things I was kind of working on. And yeah, let's see. So the first work is about, like, I started with organic anodes, and this was the paper on the right, like if you see here, and this was my abstract art. So if you like art, honestly, you can make a lot of money. So that's another career path we can talk about later. But then, yeah, um, but this is something I made using PowerPoint. But the topic was donor-acceptor-based conjugated polymeric active material with enhanced pseudocapacitive contribution. So if you look into graphite, like there is later on a slide which I should have put it in beginning actually, now I realize. So the graphite what happens is, in very simplest sense, again, if I have to say, think about lithium ions as tennis balls and graphite as the drawers, okay? So you are putting balls into these drawers, but you can put the tennis balls into the drawers one at a time. Like only after one drawer is completely full, you can go to the next drawer. So that is a basic kind of very basic explanation of how lithium storage takes place inside graphite. So that is, and the process that happens is an intercalation mechanism. But the materials I worked is a pseudocapacitive. So pseudocapacitive is some amount gets stored in the layers. Okay, so graphite structure, if you are familiar with, it's more like a stacked layer, right? So the lithium goes into the between those layers. But in pseudocapacitive, some of the lithium ions are stored on the surface of the material, and some gets into the layers. So that is it's like a dual process. So what the advantage is, of course, it's a faster process because supercapacitors, if you are aware of the surface storage, I mean, like the energy storage takes place mostly on the surface. So that is a fast process. And at the same time, the pseudocapacitive is even in the between the layers, there is like some amount of charge that is getting stored. So it follows both the processes. So not completely capacitive, not completely intercalation. So it's called pseudocapacitive. Now, the design strategy idea. So I can actually just talked about the reaction. So you take bithiophene dicarboxaldehyde and a benzene tetramine. So you see, like an amine reaction can take place from this side, from this side, from this side, and from this side, something like this, okay? And this again can react with another amine of another benzene tetramine. So this is like there can be some porous structure that gets formed. And it's a very simple process. So in the end, the structure is somewhat similar to this with lot of unreacted, I mean like the normal linear chains also. So this is like a part of the whole thing. And because now there is if you see there is a in the proximity the sulfur and the amine, I mean the nitrogen is there can be a donor acceptor interaction between these two. And so what happens is the charge transfer across this chain is very fast. And that is what I mean when you say like low redox potential. So the lower the redox potential, the faster the charge. And of course, there is a conjugation. So the whole material is conductive. So there is no, that is one of the key properties. So if you take a normal polymer like PAA or PVDF or like polyacrylic acid basically, or polyvinylidene difluoride. So those kind of polymers, they are very non-conductive. So if you use them as the electrode material, there will be no charge storage because the whole thing is not conductive. So ion cannot move. So I need a conjugation, a continuous conjugation. And that is what makes the whole this kind of material very suitable for anode material. And yeah, so, and on top of it, because I have sulfur and nitrogen, those two, I mean, like away again, like nitrogen has lone pair, and sulfur also has like the electrons available with it. Those can actually bind with the lithium, incoming lithium, because remember, incoming lithium is more like an Li plus, so it doesn't have any electrons in its shell. So now the sulfur and nitrogen can also coordinate with the lithium. So that makes the whole I mean, like the whole charge capacity of these kind of material is very high. And of course, there is like a little porosity. The porosity part, what happens is the lithium diffusion can take place, and so the process is again faster. So after the synthesis, of course, what any organic chemist or anybody would do is do some certain amount of characterization to be sure like the material is what you expect. And this is a basic characterization of the whole thing. Like you do an XRT, uh, you do an ATR, FTIR, and then you do TGA to understand the weight loss and how it is behaving, and of course, like an NMR, the solid state NMR. So these kind of materials are highly insoluble in normal solvents, and that is why we go for an SSNMR, like the solid state NMR, rather than a normal NMR. How most people do, like using the enema tube. So this is the TM image. But like I was saying, the most important part is this, like a normal DFT calculation, if you do and find the homo-lumo gap, band gap, it is very low. And this is what like the redox potential is very low. Now, because of this low-lying LUMO level, okay, which is much lower than EC and DEC, the chance, I mean, the probability that the electron is accepted into this orbital rather than this orbital is higher. So what happens is excessive electrolyte reduction doesn't take place. Remember, electrolyte reduction will anyway take place. It is like an inherent quality of any battery mechanism during the first cycle. But at the same time, because it is like, this is very low compared to this, the LUMO will accept, like there's a higher probability that the electron comes into this orbital rather than this orbital. And so there is a lesser amount of electrolyte reduction that takes place. So after the material is made, because like the main objective is of course to look into its battery performance. So the slurry preparation, it's something that I followed throughout my PhD. This remains the same. Okay, that you make the slurry using this combination, then coat it onto a 20 micrometer copper foil using a 0.1 Doctor blade, and then dry it. Of course, like 0.1 is for like the half cell studies. So half cell studies, you are using lithium metal anode as the reference. So any electrochemical system, you'll have a reference and a counter electrode. So in my case, in case of a half cell, actually, you are always having lithium metal as the counter and the reference electrode. At the same time, if you are using a sodium metal, it is a sodium ion half cell. So that is the basic difference. And all the potentials that we actually put forward, or we actually, I mean, like look into is in comparison to lithium plus. So this is a common process, and 0.1 Doctor blade is for the normal coating. So if you are looking into full cells, of course, the mass loading has to be higher. So Doctor blade, that the Doctor blade is basically a kind of a small bar or a slab which has like the distance between the ground and the slab is like this. So it coats around that much. So if it's higher, so more coating will take place. So that is for full cells. But then this is a basic procedure I follow for my half cells. And after fabricating the cell like a coin cell, okay, so coin cell is very basic way to study a property of a material. Like you can slowly go into looking into a pouch cell, and then probably even like stacked pouch cell, prismatic. So the ones you see in your mobiles, or then you can look into like a bigger format of the cell like the cars, or like a cylindrical cell that we are aware of. But the very basic thing we study using a coin cell. So there are again different types of coin cell you probably would have seen. So the one I use is 2025. So 2025 is basically the distance, like the whole cell coin cell's height is 25 mm, and the diameter is like 20 mm. So that is 2025 okay. And so that is a 2025 cell. You do an impedance study. So this is a regular procedure I follow, because that is how I base my studies. Like everybody has a way to do studies, and they want to read how their data, I mean, like what is the next experiment. For me to read any or to do any understand any material properties, I first do an impedance study. So again, it has its own flaws, that actually the impedance study should be done, very ideally speaking, with a reference electrode. uh, and the counter electrode should not be polarizable. So those are like, once you keep getting experience, you develop these kind of thoughts. But then this is with lithium ion as as the counter and the reference electrode. But then it gives you a general understanding how the material behaves. So if you see, uh, so after doing an impedance study, that is PES before CV, you run a CV experiment, because over there in the CV experiment, you are actually forming an SCI. So as I was saying, SCI will be inherent in every battery. So irrespective of you have any kind of material on top of the anode. So electrolyte will anyway degrade, because at a very low potential, anything kind of it will accept an electron. So so every material can accept an electron at a potential, right? So electrolytes will also accept some electrons, and then it will degrade, it will break down in different ways. So there are still studies going on how they break down. So yeah, and then there is an SCI which forms, and this SCI is very conductive. Okay, so it is electronically insulating, so and but ionically conducting. So what I mean is the electrons, so electrons are flowing from the outer circuit, right? So they cannot pass into the electrolyte. Like there is this anode material, there is this SCI on top of it, and then on this side there is electrolyte. So like SCI is very important because once the electron come here, they cannot pass this SCI which is there. The electrons come into the battery from the outer circuit. They cannot pass through this SCI, and so more electrolyte reduction doesn't take place. That is a very important quality or characteristic of SCI. So because of that, SCI formation is a very important step, and so much research is being done how to optimize this SCI itself. So once the SCI is formed, but this is again, as I told, SCI is ionically conducting. So the lithium ions can pass through. So there are again different studies, and still studies are going on how lithium ion is just passing through the SCI. So yeah, but then SCI, it passes through the SCI. So it is important. So now it is the whole system is more conductive. So because of that, if you see the resistance decreases after the CV is there. So after the CV, an SCI is formed and the resistance decreases. So once that is there, done, so this is our basic A and we understand. Then we can do actually CV at different scan rates. So once we do at different scan rates, so there is something like a power law. I'll not go deep into that, but just remember, closer the value to 1, more the capacitive, the behavior. Okay, so if you see, look into capacitive materials, okay, completely capacitive, their B value will be something like around 1, 0.9 to 1. Okay, but this is like, as I told, pseudocapacitive, the value is around 0.9 again. So with a very high pseudocapacitive behavior, which also means that surface storage is very higher. Okay, so if you look into this D picture, you'd see there is another equation you can use. As I was like, I will not go into this, like deep electrochemistry, some mathematical things we have to do and then get into the whole thing. So, but then in simplest of the sense, if you see at a very slow scan rate, there is like 51% of the current. So anytime like a reaction takes place, there is some current, and that is what we are measuring. So uh, there is 51% which is capacitive. That is like the 51% of the current that we get, we are seeing it's stored on the surface of the material, but 49% is being stored inside. So because this is a very slow scan rate, so there is enough time for the ions to actually go inside the layers of the polymer and then get stored. But then as we increase the scan rate, okay, like to 1, which is like 10 times, so what happens is there is not enough time for the ions to go inside the layers of the polymer. And so 75% of the current that we are observing is from the surface storage of the a surface storage, right? So that is one of the things you can observe from this graph. And very less, only 25%, around 25% is getting inside, and that is giving us a current. So that is the basic understanding with pseudocapacitive material. Now we have recorded that, okay, fine, we have a pseudocapacitive material, but how is its performance when we are uh, in a battery, like at different current rates? Okay, so if you can see, it's a very high current rate. Okay, if I have to directly come here, so at 100, this actually I have done, so that image I have not put, but then at 100 the capacity is 850. So the normal graphite, if we have heard, like it's 372 mAh by G. Its capacity, 1 C of graphite is like around 372. But this is like 850, and even at like 5,000, okay, which is like around 10 times or more than 10 times graphite. So 372, 1 C is 372. So I mean, like 10 times is around 3,700. I mean, like, yeah, 3,700 kind of a thing. But it's more than that. The current density, like the amount, the rate at which we are pushing in the ions is like 10 times. But it's still able to give like 205, which is quite good for such materials. And it is also like very stable up to 1,000 cycles. So it is also showing very long cycling stability. And that is very important when we are looking into new materials, because graphite has its inherent issues, that it has this limited capacity. At the same time, it is not very stable up to very long cycles. So it has its own problems. So, and we are looking into new materials. And then we do a post-mortem XPS study to look into the interface. So yeah, and that is one of the things we can look into if we are interested at the SCI itself, and we can see this as such, the carbon, nitrogen, and sulfur, because I mean, like, the nitrogen and sulfur actually come from the anode. But even after the SCI formation, if we can penetrate the X-ray so deep that we can see the nitrogen and sulfur, that means the SCI is thinner than around 10 nanometers. Okay, 5 or 10. It is between 5 or 10, because the penetration depth of a normal X-ray aluminum source is around 5 to 10 nanometers. So if we can go deep into the, like, you can break into the SCI and detect the elements which are like from the anode itself, that means the SCI is less than 10 nanometers. And yeah, you can also look at the volume, like you can do an FESEM of the cycled electrodes, and of course, like the volume change you can calculate, like you can take a pristine and then take a 200 after 1,000 cycles, the electrode, and look into the difference in the volume expansion. And then, like, because such porous materials, now what is the advantage of such porous materials is that because of this porosity, they can actually not degrade fast. So it just allows the ions to pass through them more easily. And so in that way, what happens is that the volume expansion is very less. If you look into graphite, what happens is, like, it is stacked. So when the lithium ions are coming, these kind of move apart. And once the lithium ions has passed this channel, it comes back. So this continuous thing, when it happens, the graphite kind of breaks down, and at faster rates, this is very difficult. This whole process is very difficult. But with the porous materials like this, or any carbon porous material, what happens is that because they have pores, they just easily allow, okay, the whole ion conduction to take place within them, and that is much simpler process, and so the volume expansion is not very high. So that was like about my first work. The second work was about using such polymers, um, using such kind of polymers as templates for carbons. So now I was talking about the such polymers can have pores. Okay, so what happens is now, like, yeah, so this is a basic graphite storage mechanism. Of course, it's very simplified, but then this is a basic mechanism. But this is how a porous material it will help. So now what happens is that for making such porous materials, generally template methods are used. But then template methods are really difficult. I mean, like, it is time consuming and can be like, it can be very costly, and also it is not very environmentally very safe, because you use a lot of harsh chemicals like a KOH, which is a very strong base. So the other way of doing the same thing is take a self template, okay, which already has pores, and just make a carbon out of it. So this process is quite simpler. And even though the difficulty at this moment is it may not give us a precise control over the pore size, but still it works to a great extent very nicely. So again, if you see, my starting compound was bithiophene dicarboxaldehyde, but this time I wanted little bigger pore size. Okay, so I took a bigger second monomer, which is a melamine. And then the reaction, after the reaction, so you see the pore structure can form like this. Okay. And again, it's more like a donor acceptor because of the nitrogen and sulfur being in such vicinity. And I studied its property at two different temperatures. Like I carbonized the whole thing at 600 and 800, and I could get carbon. Of course, like if you push anything above 550, 600, the organic structure breaks down and forms carbon. But when breaking down, because it has pore, it'll kind of maintain it. Okay. And yeah, and such innate porosity and high surface area. Because of high surface area, we get high surface area materials. So again, high surface area, why I'm talking about it is because more charge can get stored on the surface, and the higher the surface area, the higher the charge storage. So we can have higher capacity. But the downside is, of course, that higher surface area means such high surface area is also getting exposed to the electrolyte. So the electrolyte reduction will also be high. So we can optimize that. That is another separate topic altogether. But here I was just studying material properties. So yeah, this was the thing. And the other thing is having dopants in the carbon structure. So what happens is dopants are very important because not only do they, increase the electronic conductivity of the whole system, but also can store. Okay, and based on like how much percent of heteroatom is there, the performance can vary. And generally people use, like when they are making porous carbon, they use like urea, thiourea to add nitrogen, sulfur, very cheap ones. But here we are having a self template, like when already nitrogen and sulfur is there. So when you are carbonizing, they can't simply like vanish, or something gets incorporated into the system. So even out without addition from external source, such high amount of heteroatom was available. And we did more studies to understand the surface area, which was pretty high, and the mesopore volume, so the volume of the pore, which was formed, was also very good, and so was the mesopore surface area. So these were calculated, and yeah, and it all in all, like the whole thing is, uh, there are materials which give, of course, better results, but then they are using different kind of starting precursors and different methods. So this was like in itself new, because self-template methods for battery systems are very few in literature. Few have been used for electrocatalysts, but not really for battery applications, especially for sodium-ion batteries. And this was my project about. And so more things to understand. You can see like at 600, there is lesser pore structure than 800. So what happens is 600 carbonization temperature is not very high enough sometimes. And so the pore structure, like it is not very porous. So when the carbon structure is completely breaking down, 600 to 800, if you go, more carbon structure breaks down. So there is more amount of volatilization that is taking place. So you see more porous structure. So that happens if you keep increasing the temperature. That happens. But if you go to something like 1,000 degrees Celsius, which I have done, but I have not reported because it was not required, the amount of sulfur and nitrogen decreased drastically, because they start. I mean, like even if you are going from 600 to 800, if you see the the nitrogen and the sulfur ratio starts decreasing, and that is because most of them get volatilized. Okay, but if you go more than this becomes around, if I remember it right, around 8%, and this becomes like 0.3 or 0.4% at 1,000 degrees. So that is not very appreciable. That is not what I was looking into. I wanted some amount of dopants in my carbon system, so that these two temperatures were serving it right. And so after that, the basic uh, CR 2025 cells, and the basic amount of study that I do to understand the diffusive and capacitive current. And this was with 600 lithium-ion batteries. If you see, the capacitive current slowly increases, and there is some amount of diffusive current also. But uh, to give a comparison, capacitive current is just 38% over here. Suppose the surface area is low for 600 compared to 800. You see the increase, like from 38% it increased to like 65% just because of the surface area. So capacitive, and that is what like having a higher surface area can do. It can increase the amount of capacitive current, so the fast charging applications are more better. And that also can be seen like the B value. So as I told earlier, B value from the power law, closer it is to 1, more capacitive. So here is 0.74 and here is 0.87. So yeah, so more, so definitely 800 is more pseudocapacitive. So it is better for fast charging applications. And I did more studies to understand like the activation energy. So what you do in activation energy is basically you do an impedance study at different temperatures. So I do like 20, 30, 40, 50, 60. So those temperatures I record, like I do charging, and while discharging, I mean like not discharging is like all right. In I would say like during the lithiation process, what happens is that at zero point 0.1 approximately, lithiation starts in any carbon-based material, zero point 0.1 or 0.2, around that. So I stop at that potential at that temperature and then record an EIS. So after doing that, I deconvolute the EIS spectra. So there are like R1 and R2 components. So there will be like, if you look into the whole thing, there will be like a slower process and a higher process. Like once you start doing EIS, suppose in your future studies ever, you will see like there will be like two components most of the times. Okay, so there will be one dominant factor. So my idea was to study the ion transfer through this dominant resistance factor. And so because now this 800 had a higher surface area and higher pore size, what you can expect is that there is higher number of contact points on an 800 surface. And so in turn, what happens is it's an easier diffusion that is taking place. And the diffusion coefficient is basically the way like the amount of diffusion that is taking place within the electrode material. Now if you remember, like the volume and the surface area in the 800 carbon was higher, and so the diffusion process is pretty high compared to the 600 one. So this is the, and then when you look into the fast cycling, okay, the 800 always gives a better result because of its higher pore structure. Like in every case, if you see 1, 2, 5, and 10 ampere per gram, I went up to that, and this was pretty fascinating for me. And one more fascinating thing was the exit to XRD studies. So if you look into this de-spacing, okay, you do a normal study, like you stop at 1.5, 0.4, and 0.02 volts. You just stop the battery after charge, after lithiation at that potential, and you just take it out and you study your XRD. So if you see the d-spacing in 600 change from 5.2 to 9.2 angstroms, okay? But in 800, it changes from 5.95 to 7.7. So the difference over here is pretty low compared to difference in this. And that is because now there is a smaller pore structure in 600. So when the lithium is going, okay, more and more lithiums are coming at 0.02, the pore expands very highly. Okay, but in case of 800, because already the pore structure is very high, so the expansion of the pore is pretty low. So that is what, like I mentioned in the last point, that is higher pore volume better accommodates the volume expansion. And that is why also we see like a better performance in the battery. And then I did the same thing with like a sodium half cell. And if you can see, like the B value again is 0.7 and 0.86. So clearly higher, highly pseudocapacitive, this 800. Of course, like because it's, I mean, like this is kind of expected because it is already having a high surface area compared to 600. So it is more like understood, but this is more like a quantification. And then I did the similar kind of studies with dissolution energy and studying its rate performance at even 1 ampere per gram. And yeah, I mean, like the studies kind of gave like something expected. It was more like a quantification process for me, I would say. But in every case, like the diffusion was better in 800. The dissolution through the dominant resistance factor was higher in 800. So the carbon, and the performance as such in 800 carbon was higher. So the next thing was, such carbon materials are good in half cells, but are they really good in full cells? So the process I did for like both in this case, like with an NCA cathode, and it did give a very good capacity. Uh, of course, like 800 getting a little higher capacity because of the reasons already mentioned. But for sodium, 600 didn't work at all. I mean, like if you look at the performance also, like it is almost like touching zero after 500 cycles at 1 ampere per gram, and the the capacity is pretty low at very high, even at very like 1 ampere per gram or 0.75. It's pretty low. So I just conducted for 800, and it gave a very decent capacity, I would say, with like at a current rate of 0.375 mA per centimeter square. Um, and yeah, so this was again the studies with more or less the carbon materials in both lithium and sodium ion systems. And this was the XPS study to study the carbon, how the SEI looks like after the cycling. And this was the FESEM images. So there was like higher amount of crack that I was observing in case of 600 compared to 800. So this was a good kind of an observation, I would say. And the last work, this is under review actually. So yeah, this was about having a bio-based boron-containing polymer as an at the interface. Okay, so we started with organic and then went into carbon, and then I'm going into like carbon and organic, like both. That was my storyline for my PhD. Like you can look into different materials at different points and at different projects. So can we actually increase graphite? Can we actually make the existing material graphite? Because graphite, as I told, it's a very slow process at the interface because of the mechanism. So if we have something like a boron, if we have like boron is electron efficient by nature, so it can help in easier desolvation is what I hypothesized. And so I mean, like we can coat it using different polymers, but I wanted the whole polymer to be bio-based because it's more sustainable, so you can produce more of it. So the because it's of course like the work is under review, I have not kind of put the structure of the polymer. Sorry for that, but then yeah, but then after kind of the whole process which I have mentioned over here, I could coat the graphite with the boron-based polymer, and this was the coating basically. And this is like if you can see this TEM image. So this is around 6 nanometers actually, because this is amorphous. So polymers are amorphous in nature. There are like this is an amorphous polymer. I'm pretty sure. I'm pretty much I'm sure about that. So once you pyrolyze it, so an amorphous material, the method I followed for pyrolysis gives an amorphous carbon. So you can see this is amorphous, and this is graphite. If you can see, like it's very much stacked. It's very that is one of very characteristic. So yeah, you have two different layers, and this is what shows the coating has taken place. And even like there was a little bit of amorphous nature, which was not found in graphite. Graphite is this one, yeah, control. So amorphous region, which was found in this. This is an XRD plot. And after that, the basic EIS tests to understand the electrolyte deterioration and the whole impedance studies and the diffusion. Also, if you look into the graphite, normal control was pretty higher compared to the cab coated. So the name is like cab, basically the graphite boron. Okay. So the cab graphite, which had pretty higher diffusion coefficient and also the activation energy, like the desolvation was pretty much better. It like changed from minus 57 to minus 46.56. And these values are very much close to the normal ones done by Yamada Group. So Yamada Group is a very popular group in Japan. They are from Osaka University. He does a lot of interfacial studies into right now I was reading so solid electrolytes. So they do a lot of interfacial studies, yes. So the value they did for graphite was around I think 50, 60 or something. So this is pretty much close to that. And the crab graphite when we had our boron polymer, so they decreased from that to minus 46.56. So yeah, so that is basically the whole thing. And even at like very high current rates of 10C, you can see the performance was like 80. So the with graphite, it's like normal graphite, it is just 25. 10C is like really fast, right? One C is 372, 10C decreases to like 30, around 30. But then with when we are coating with graphite, I mean like a cab, we are getting around 80. And that is also partially because the amorphous carbon also stores a little bit of lithium. because it's also carbon, right? So it can also store it. It can also store lithium. So that's why we are also seeing a little bit higher capacity. And then more into differential capacity curves. So we at 0.05 C at a very slow rate, we are looking into the degradation of electrolyte itself. So if you see like in normal graphites, all 3 cycles there is some amount of degradation that is taking place, but when we are coating it with cap, just a very slight amount of degradation in the first cycle. Of course, this is like no, this is like you cannot completely just tell from here, so other studies need to be there, so that is why like we have done like CV and stuff. But yeah, this is more like another way of kind of looking into the whole electrolyte degradation, and onset of electrolyte degradation was very was there, but then after the first cycle, there was not much changes we were seeing in the dq by dv curve. So you would see like a lot of other kind of peaks if there is any reaction that is taking place, any chemical reaction, it'll be like a peak. So yeah, so in graphite there were a lot of peaks kind of a thing, but it not when we were kind of coating with cab graphite, because I think one of the reasons we put in our paper was because when we are coating it, what happens is the diffusion is easier at the surface, and the dissolution, actually not diffusion, dissolution at the surface is easier. And so once the SEI is forming on top of a boron-based interface, it is much more stable. And so what is happening is like no much electrolyte reduction is taking place. But with graphite, the SEI is not very stable, and so a continuous degradation is taking place. So that was like about it. And then with full cell, like full cell is very important when you are looking into carbon systems. So it gave very good capacity even at like a slow current rate of 0.75, and even very fast, like it's like almost double, right? So it was giving a very good mAh. Like these are all with coin cells. So if you are able to reach like 1.52 mAh with coin cells, it's very good for the loading that we are doing. And then we looked into SEI, and it was rich with all organic and inorganic as we expect. So that can possibly help in better uh, transfer of lithium ions. So that was like all my PhD works, that and some collaborative works with different labs. And so this was like from a lab with an exchange student. These two papers from India who had come, and then this was with one of my lab mates, like which I worked on binders. And Mm, yeah, so most like I've been really like lucky enough to be working in such nice places. So this is my university in India. So I worked at this university, Satyasai Institute of Higher Learning, and then I moved to JIST, so Japan Advanced Institute of Science and Technology, and then right now I'm working at Uppsala. So yeah, and these have been my funders. So during my PhD, it was mixed. So this is a scholarship that is given to you for 3 years, and now right now I'm my professor actually got the funding for from Swedish Energy Agency. So that is a project I'm working on right now. And yeah, thank you. And if you have any
Thank you
questions,
so much.
please, yeah.
Thank you so much. It was really incredible speech. Actually, uh, from my side, I learned a lot of things. Um, I thank you. I really appreciate it. I have a question. Like, uh, maybe you explain it, but I missed.
Yeah, sure.
I didn't catch that. Um, what is the major differences between like when you do it with sodium-ion batteries and lithium-ion batteries? Like,
Okay. So if we have to compare, I can actually give you a little comparison. Yeah. So if you see now, if you put like in a very simple sense, sodium ions are bigger, right, than
yeah,
lithium ions. So if you look at the capacity itself, it's around like even with 800, it's at 1 ampere per gram. Uh,
yeah,
the the diffusion is not great within the sodium ion. Sorry, so within the 800, so the capacity is around 300. I mean, like it decreases because like the it keeps cracking. Sodium ion is bigger. Okay, so we
mm,
need even higher pore size. But when we look into like this system, 1 ampere per gram, like with retention is quite better. Okay, so
okay,
and that is one of the major differences. The retention in case of lithium ions is always much better than case of sodium ions. And
Okay,
that is
thank you.
because like, yeah, the pore size is the same. I mean, like sodium is bigger, so it will need a better pore size to have a better diffusion within the material, or else it will keep breaking the molecular structure apart.
That was my second question, but you answered it. So I
All right,
was
okay.
gonna ask about like their like size difference and its effect. Like, so thank you so much. So guys, do you have any questions about the presentation?
I have one question. Nice to meet you,
Yeah, you can call me Sai.
Saitra.
Yeah, you can
Rata,
call me
yes.
Sai.
Actually, you have a lot of experience, especially it can be a lot of voices in that in my.
It's okay, it's
Um,
okay.
Actually, Shay, you have a lot of experience, especially in this field, battery field, and during the doctora and postdoc, you are working on battery field. And apart from this studying, this presentation, actually, I want to learn some things from you and maybe give advice for us. And finally, therefore, actually, most researchers are working on batteries, especially sodium-ion, lithium-ion, solid-state batteries. Uh, and Musab and me, about 2 years, and Musab maybe 2 and 4 years, we are studying in this field. And during the undergraduate, and now I am studying a master program. Uh, Actually, we want to study, we want to improve skills, battery field. Based on our discussion and your experience in this field, which battery technologies do you think are the most promising to focus on impactful research over the next five
Um,
and 10 years, and why?
uh,
Actually, most, especially Germany, most researchers uh, are working on solid-state batteries
Mm-hmm.
and dry cutting systems,
Mm-hmm.
and and they want to improve different different skills. You say yes, and I want to learn some things from you.
Okay, so I would say after completing your master,
um,
this is completely. Oh, yeah, yeah, yeah. Ahmed?
by the way,
What?
I'm sorry to interrupt. I was going to move forward to these kind of topics. So,
Sure, sure,
if
sure.
there is no if there is no question about presentation, so directly we can start with this question. Actually, I was going to ask that question as well. So, like, what would be the like next trends? Like from your from based on your experiences, what would be your advice for us? Like, what would be the best skills and what would be the best battery technology or battery type to continue our research and our career as well?
So I would
Yep.
say, okay, it's a completely personal opinion. I would say first talk to as many people as possible. I mean, like this platform, when actually Ahmed shared, and then I was going through like the YouTube videos, like of previous speakers, and then like the Instagram page. I would say it's a very good thing that you are connected, because what happens is awareness is one of the things. I think most of people, like when I was doing my master's, I did not have much awareness about, like, batteries, and then you can do internships outside, all those things. So it's a very different thing for you all right now with internet so much. So I would say be aware is a very big thing. Second thing, what kind of career are you looking into is a very another great I would say starting point for what kind of batteries, if you're looking into battery research, okay, or any kind of research, what kind of path you're going to take. So after completing masters, I have not done it, but if somebody asks, I do say this: go for an industry for 1 or 2 years. If okay, go for an industry, battery industry or any kind of industry, go for 1 or 2 years. You will see the difference. Okay, you have a battery experience, you can always apply to industries and get into an industry, be it in Turkey or be it in Germany or be it in Sweden. Anyway, it's gone. Northvolt is gone, Altris is almost gone. So I mean, like, it's bad over here, the battery industry. But then like, look into good industries in Turkey or Germany, for example. They have been good. But then there will be so many startups also you can look into. But do work at that scale. Okay, doesn't matter the technology. If they're working with lithium sulfur, solid state, sodium, or lithium-ion batteries. Okay, if you are having an engineering background, BMS, thermal management, things like that. All right. So, but look at that scale, how the things are done. Once you know that thing, okay, once you know that thing, you will yourself have a clear idea what academia needs. This is my understanding. I have not done it, okay? But anybody asks me, I do say from this perspective, because I think that is something which is missing after talking to my friends. They are saying, like, it's not like we keep proving. I made materials, okay? Tomorrow I make better materials, but what is the use? How do I actually apply it in industry? Right? If you want to patent it, I mean, like, you can make a small molecule, try to patent it. Okay, but how does actually industry look? So that kind of an understanding, if you are having, but yeah, I'll complete this first. That is important, okay? To which field you will go into. So if you think, I mean, like, if you're working on electrolyte optimization, suppose in an industry, you will know what is exactly like the issue with the electrolyte at an industrial scale. And so at a fundamental level, what I should be doing. Okay, if I want to pursue an academic career after that, okay, do a PhD, what problems will I be looking into? Right. So that is one of the major, because see, when I design my experiments, I read. Okay, I read papers and then I understand maybe the issues which are underlying. But I have never seen those issues underlying. How do I believe those? Right. Somebody says graphite is bad. Like, I mean, like, it's bad, but then uh it may not be the case, because graphite, we are still using graphite with a little bit of silicon now. Right. So for anybody, I would say just go to industry 1 years, 2 years max. If you want to do PhD, if you're sure about it, that you want to have an academic career for at least 4 years, like, but have an industrial experience, know how we are working, what problems are you looking into. Industries have very standardized procedures, right? So those things you'll get exposed to. So my experiments may not be what experiments industries are doing. Something, again, I really not like having, because industries have very standardized procedures. I do something by reading papers, and reading papers, you do not know which one to trust, which one not. So you go for good authors, maybe that is one way to select. But industrial experience is important. But if you have decided that you want to have an academic career, come whatever may, okay, like, it doesn't matter how the industry is working. I want to study. I want to study the batteries in whatever form, either make materials or study existing materials. The important thing is how you want to study. Do you want to go for bigger papers? Okay. Or do you want to go? I mean, like, these are again two different directions. This is what is all my experience I have seen. Okay. I'm also trying to transition. I would love to be an academician, but then somehow I feel like I should have been in, I feel more inclined towards industry at the moment. But remember, what do you want? Like, you want better papers. That is one way of being in academia. Okay. You're showing your results in very good papers, or you want to study very nice good amount of studies you want to do. And, like, if you suppose, if you read one of the professors, Eric Berry, Ahmad will be knowing, right? He does experiments on FEC, VC, okay, additives, normal additives, right? And he does that. He still studies those, and his papers are not in, like, very, like, nature and stuff, but then those studies are so very important. Okay, so very detailed, so very nice to read, actually. Okay, and that is one way. But then some people do not believe in that. Okay, if you go to a material development lab, they will aim for bigger papers. Okay, if you read Nature materials, there will be not like hardly any studies like this. There'll be like new materials development. So, and new materials can be applied to anything, irrespective of your future goals. Okay, so if you are making a new polymer, it can be in lithium sulfur, you can apply. So that choice again, like, so the next step comes which battery field now. So if you want to be again in academia, look into fields which is paying and giving you grants. AI at the moment is like that hotcake. Okay, gets funded a lot, even for battery designing. AI is, that is my, again, my perception, okay, of things I have seen. See which country you're going to work and what that country needs. Okay, for example, Swedish Energy Council, they're seeing if the whole idea you are writing to, like this is from again speaking to few of the people over here, uh, the idea you're proposing, is it good for Sweden? So something which is good for Sweden may not be good for Turkey. Something which is good for Turkey may not be good for India. So it may not be funded. Right. So look into the field, and this is all my personal observation. Okay. So look into the field, because end of the day you want funding, right? I mean, like you can't do your research without funding. So look into the field which is paying for that country. All right. And then do your research based on that. Or so that will give you like a higher impact factor papers also, because you'll be doing something very new. Or forget everything. If you are very much focused on doing some basics fundamental studies, like Eric Berry, who is doing great job, okay, you can still get funding. Okay, given that you know how to write, you know how to write your grants. So that is one of the things. Okay, and of course he's doing great things. He is like, I think in Inti's project is about, I think he presented like understanding like through acoustic modeling kind of a thing. He would determine the degradation. So those kind of studies. So there are people over here doing very nice studies like basics understandings, but very new methodologies. So there is a lot of paths. So once you get into the field, it will open up. Okay, so don't get overwhelmed like, there are so many fields, and then there is so many things to do. But as you get into the field, try to remember these things. I would say try to look into these things so that if you are pursuing an academic career, it becomes a little more smooth. Okay, so that'll be my suggestion.
Thank you so much. Actually, those are great points. I was struggling with like making decisions about these things because I want to make science, but which is driven by reality and the industry. So I want to make science, but at the end of the day, I need funding to pursue my academic research, and also everyone wants to see its work uh, being applied in the real life and industry. So, for example, right now in my internship, I talk with engineers in the factory. So there is often misunderstanding between like research and development engineers and production engineers. So research and development engineers, they are trying to like find a new formula and some new ideas, but they are not aware of the like production sites. So they always fight each other. So
Yeah.
whenever in the factory, whenever R&D department suggests something, so our production engineers say that how can I transfer that chemical? How can I like buy it, transfer it, and how can I operate within my current like setup, like process flow. So because of that, like yesterday we were talking about it, and one of the engineers told me that you know what, I'm right now a production engineering in this factory, but my long-term goal is to pursue PhD, then move forward to industry, come back to industry again. That is a really great idea. I really appreciate it. So maybe the next question would be like, when you look at the whole world, battery, like from the battery research perspective and industry, so how do you see the like part of like the part of the world, like for example, as I see, like in Nordic side of the Europe, they are really good at science, like fundamental science, like trying to find new materials, chemicals, but they don't look like in industry part. So like when you compare the continents and like main battery regions, what would be your comment for each? Like, for which profile do you recommend that place? Because like most of our followers and most of our team members right now, me as well, we are trying to find a place to pursue our battery research and career. So according to our needs and aim, the direction should be different, right? So what would be your comment on that?
So, okay. Now, what I know of is there are two kinds of things you'd have heard. Like there is a research institute, like a RISE. Okay. So when I was working in Japan, I was in a research institute. Okay, Japan Advanced Institute of Science and Technology. So those kind of places are generally, as much as I know, okay, like this is not again like foolproof kind of a thing that you can talk to more people about it. But then from my experience, those kind of places do applied research. So in my lab, like my previous lab, it was more about studying very new materials, like I showed you, and developing new materials. So that was like the main focus. But in universities like Uppsala University and things, it's more like doing a fundamental study. Okay. This is like universities try to do this. I'm not very like 100% kind of like confident on this statement which I've heard. Okay, but then somehow I do, I mean, like from a research institute, I've come to a university. I do see that kind of a research because if you look into the recent papers that have been published, for example, in different universities, if you take for that matter, that have been studying more in detail about something which is established. Okay. So there may be like papers on why PA is a bad binder at 2%, but is a very good binder at a 10% or something like that. Okay. But then a research institute will not care about PAA. It doesn't, for them, it is about making a new binder material which works very nicely at 2%. Getting the whole thing, right? So, and that binder may not be industrially straight up today. It may not be applicable, or in future it can never be applicable. In my previous lab, we also have like few patents, but then it's like when you go into industrial scale, okay, it becomes difficult. But then we also have a patent from our previous lab, which the industry was very interested in when it came to like making additives. So that can happen. So, but then research institutes try to make a tomorrow kind of a thing. Well, while universities do study something like current materials in depth, because even optimizing the current materials in depth can result in a great thing, right? Like if you optimize a PA is already commercialized. So if you optimize at 7% rather than at an 8% or a 6%, okay, so currently suppose you are using 10, but you can optimize it at 7% somehow. Okay, so you are adding that much higher capacity to your battery because you're adding more active material. So I think it depends what is your objective. How do you want to see your research? Okay, do you want to make new materials? That is fun. Okay, do you want to study more materials? So it doesn't matter. I mean, like it's optimized, it's not. I didn't study like 80% what happens, 60% what happens with my polymer, 50% what happens, 90% what happens. I just wanted to study at 80% this new material, how it behaves, what is the charge transfer. Okay, and if there is any charge transfer, so not but like I had done a monomer kind of a reaction, small reaction to prove the charge transfer that is taking place, okay, by pi-star transition. So simple like reactions and new materials. It depends what is like your aim. How do you want to look at your research? Do you want to look at, so yeah, I mean like industry end of the day, if you want to transition, it'll anyway help you. Okay, you are working with anodes irrespective of in academia or in I mean like more industrial focused. So it doesn't matter. Also try to look for, I would say, if you want to industrial PhDs, if you want to go into industry, that is very important. Uh, because industrial PhD, you will be working closely in association with industry, so you will be knowing what you are looking into, like what the industry is looking into rather. So those are again very good options, I would say.
Uh, Thank you so much. And last question is, um, I want to learn about like from your uh, experience. Like you were in India, you study your bachelor and master as well. It is integrated program, right?
Yeah, yeah, mine was an integrated program.
Yeah, so you start with like Indian research culture,
Mhm.
then move somewhere else like Japan, and
Mhm.
you stayed there like how many years? 4 years
Yeah, three and a
or
half. Yeah, three and a half.
3.5, and then go somewhere else like
Yeah,
north part of the Europe.
yeah.
So what were the like main perspective differences like and working like habits differences between those areas? Like
Yeah, so I would say I say this like to Indians also, if you get a chance going abroad, if you do not have any limitations at like, you don't have any responsibilities, do go abroad for your PhD. Uh, India, some institutes are really good, okay? I mean, but still, they do not match the basic research institutes in Japan, I would say. Like, I didn't do in a great research institute in Japan, like by QS rankings, if you see. Okay. But I would say the availability of resources is pretty easy in all this, like even in Uppsala, if you see. India, it is little difficult, especially if you're not from bigger universities. Okay, so I mean, like bigger in the sense really big. And India, the competition is fierce. There's a lot of people, a lot of ambition, and everybody wants to do, I mean like not everybody, I mean like so many people want to do a PhD, so there is this national level exam which is really tough for me, at least for me it is really tough. So I was like, I can draft a proposal which is easier for me than crack the exam. And that's why I just was applying for scholarships and things like that. And yeah, I would still say that resources in India is little bit, I would say, difficult to procure and manage with that. So you need a lot of. But then good part is if you're applying to industry, you can have a like you can put on your CV had a good vendor relationships because you'll be contacting so many vendors for giving a good quote so that you can order. I mean, like you need not break your head on those things much and abroad. But yeah, that is one thing in India, I would say. The research, because of this, the research is slow. So in very good labs in India, maybe you will finish in 4 or 5 years. But sometimes because of this limitation, it does take up to like 7 years. So that is like 7 years of your life you are spending on your PhD. So if it is like a really good PhD, then maybe 7 years is worth it. But then if it's a okayish PhD, mediocre PhD, then 7 years is not worth it. Okay, so that is one thing I would realize, and that's why I never wanted to do it in India. Japan, I would say, because I was in a research institute, it's more fast-paced. I mean, like, and new materials is like really novel something you have to make. Okay, you cannot. I mean, like, even if there's something lab is working on, so that is really novel. So you are even though optimizing like in a certain way. So if it's like lab is working on A and somebody is coming and doing A plus B. So your task is A plus C. Okay, but the whole thing is A plus C may not work. So A plus B works, A plus C doesn't work. So now you have to find like eight, so many combinations come. So that is if the lab has a specialization. But if it is not, then you have to really find novel materials, and then for going into good journals or even decent journals and things like that. And that's little hectic sometimes, I would say. But then if you're, I mean, like if you're working hard enough and you somehow get a little lucky, also you can find really nice papers, polymers, because I was working in polymers. Uh, Uppsala has been really nice in terms of work, I would say. Even Japan, my professor, when I was working, he was very nice, super nice with the work culture. So that way I would say, blessed. Some people, I do not know, they have their own complaints, like every other place. I mean, like everybody will have their own share. So, but then, yeah, Uppsala has been really nice in that way. I would say the work culture has been nice. But difference to India, these two countries, material procurement has been much easier, I would say. And resources, the availability of resources, the availability of, the instruments or something like that has been more. And that is something which is very helpful. So when I was in Japan, so it was a small research institute, and like we have over here clean room. There is clean room, and all the instruments are there. Okay, there's nothing like you have to run. I mean, like all the instruments you would need to do a basic research, everything is there. Okay, and it's a small research institute. Not many people work, so every time it will be free. Okay, so there is like three divisions. Material science, I mean, like things you would need are almost free. I mean, like it will not be occupied kind of a thing. And one more thing, here we do pay for using instruments, if you know that. Like if I have to use SEM,
Yeah,
I do have to pay for it, like from my project, basically. Not I have
yeah.
to pay, but then project. It's a thing in Sweden, but it's not in Japan. It's by the institute.
Mm.
It's
Oh,
by the
great.
institute. So that is one easy thing. So you can just book,
Yeah,
go work, which is quite nice. Okay, here some instruments you have to run around a bit, but that's not an issue, I feel. I mean, like if you want to do, the instruments are quite nice. But yeah, I think research becomes easy when there is resources. So
yeah,
try to go to institutes where there is not enough issue with resources. Then you will not be cracking your head like where to do your NMR, and because you can't do your NMR, then you can't go forward with your research. So that will take a time. Like if you're doing your NMR after 3 months, I mean, like that is like your 3 months are gone without doing anything. This will be like reading newspapers kind. So try to go if you're looking into any research kind of a PhD kind of a thing. Do go for institutes. I mean, like pretty nice institutes all across Europe and Japan. Yeah.
thank you so much. I really appreciate it. Actually, I have a lot I have a lot of topics to talk with you, but time is up.
Hey, no
And
issues. You can just message me on LinkedIn. Yeah.
yeah, I really appreciate it. I mean, thanks a lot. So it
Yeah,
is a
sure,
great,
man. It's my pleasure.
Thank you so much
it's
for sharing valuable experience.
Yeah,
Uh,
yeah, my
it's
pleasure, my pleasure. Yeah.
it's great to have you. And thanks again. So guys, if you don't have any questions, so we can end up. Cybrata, thank you so much.
Yeah, my
Again.
pleasure, and thank you for inviting me again. I mean, like first for me, I don't know how I did honestly, but then really great that you are doing this. Honestly, I feel really happy about such initiatives because people get aware, some way, that there is being research being done, and then there are options to explore. And something
Yeah,
I do miss from my young age when I completed my master's, I just saw a few people around me who would do PhD and how they would get into all these big institutes. So they were my motivation. So that's how I could go out of the country. And then
yeah.
yeah, so nice that you are all having this. Great. All the best to you all also.
Thank you so much. All the best for you as well. See you,
See you.
guys. See you on the next episode of monthly Young Patriots Week monthly seminar. See you all. Thank you so much.
Thank you.